In order to do an analysis of a mechanical vibrating system, it is necessary to obtain the equation of motion that governs the system behavior. In this presentation, we will use Newton's law of motion and energy methods to get the equation of motion of several systems. My name is Carmen Muller-Karger. Some of the figures are adapted from the textbook Mechanical Vibration from Singular Rao in the 6th edition. This is part of Chapter 1. In previous presentation, we stated that all mechanical and structural systems can be modeled as a mass spring damper system. From the real systems, there are some systems like, for example, this motorcycle, where the mass, the spring, and the damper are very well defined, and we can do the modeling much easier. However, we have systems where the mass, the spring, and the damper can be embedded in a single element, like the case of this wing. We covered how to get, for example, the equivalent constant of the spring for a cantilever beam to be able to model that wing. And for the motorcycle, we get a system that is the mass, spring, and damper. Today we will cover how to get the mathematical model of this mechanical system. Once we get the mathematical model, which is a second-order differential equation, we will work on solving that differential equation to get a response, and finally do the analysis of this response. When we do the analysis, we will determine if our system behaves as the real system. So today we will concentrate in getting the equation of motion. For this mechanical vibration foundation course, we will work only with systems that move in 2D. This is planar motion. We have three equations of motion, adding external forces in X, and that leads to external forces are equals to mass times acceleration in X. Adding forces in Y will be that all the external forces are equals to mass times acceleration in Y. And finally, we have that external moments are equal to kinetic moments. Kinetic moment can be calculated using any of the three following equations. If we calculate moment about the center of mass, the kinetic moment will be equals to the mass moment of inertia at the center of mass times the angular acceleration. If we calculate the moment at any other point that is not the center of mass, we have two ways to calculate it. Either using this equation comes from the parallel axis theorem, and we can say that the mass moment of inertia times the angular acceleration plus the cross product between the distance between P and the center of mass cross the mass times the acceleration of point G, G being the center of mass. We can also calculate using the mass moment of inertia of the point where we are taking moment times angular acceleration plus the distance from point P to the center of mass cross mass times acceleration of that point P. This equation is very useful when we take moment about a fixed point of acceleration equals to 0, because then we have only this term. Very important to remember that when we talk about the Newton's second law, force equals mass times acceleration, mass represents a measure of resistance of motion, resistance to linear acceleration. If we have a very big mass, then if we apply the same force as a small mass, we will have a very small acceleration. If we apply the same force to a tiny mass, we will have a big acceleration. The concept of mass moment of inertia has a similar representation, but for rotation. It represents a measure of resistance to rotation or resistance to angular acceleration. If the mass moment of inertia is very big, it will require a very big moment to be able to produce a big angular acceleration. In this slide, we talked about the mass moment of inertia, which is the property that measures the resistance of the body to angular acceleration. And this is the definition. This figure, which is adapted from the text for Hibbeler from dynamics, shows the mass moment of inertia of a sphere, since it's symmetric in the three axes, will have the same mass moment of inertia, which is 2/5 mass r squared. If we have a disk that is thin and the mass moment of inertia respect to the axis that is perpendicular to the plane is 1/2 mass r squared. We have a thin ring, the mass moment of inertia of the axis that is perpendicular to the plane will be mass times r squared. And for a slender bar, if we take the mass moment of inertia in any axis perpendicular to that bar, it will be 1/12 mass the length squared. And we take the mass moment of inertia about an end on that bar in any of the axes that is perpendicular, we will have 1/3 mass L squared. And for a plate, we have that the mass moment of inertia of the axis that is perpendicular to that plate, it will be 1/12 mass, the one side squared plus the other side squared. If we need the mass moment of inertia of any point that is not the center of mass that is shown in this table, we will use the parallel axis theory. So if the mass moment of inertia of a body about the axis passing through the center of mass is known, we can find the mass moment of inertia about other axis that is parallel to that axis but at any other point, being the distance between that other point and the center of mass. An important concept is the radius of gyration, which is a measure of the distribution of the body's mass about the axis at which the moment of inertia is defined. So this point will be the same as this one, for example, and the total mass of the body and k represent that radius of gyration, and is defined as the square root of the mass moment of inertia divided by the mass. And finally, for composite bodies, we calculate the mass moment of inertia by adding all the mass moment of inertia of each independent body. It has to be, of course, at the same point. Let's now determine the equation that governs a single degree of freedom system using Newton's second law. This is the simpler system that we will have, which is a mass and a spring. We do the free body diagram and make it equals to the kinetic diagram because we want all the external forces to be equals to mass times acceleration. The external forces are the spring force that always is opposite to the motion. So if we assume a motion to the right, our spring force go to the left. And then we have the weight and the two normals. If we add forces in the x direction, we only have our spring force, which is the constant of the spring times the displacement, and that will be equals to the mass times the acceleration. If we put all the terms that have x and its derivative in one side of the equation, we get our equation of motion, which is the mass times the acceleration plus the constant of the spring times the displacement. Remember that the second derivative respect to time is denoted with x 2 dots. If we do the same exercise, but when we have also a damper, we will have, instead of having only the spring force, we will also have the damper force. It also opposites to the motion, but the damper force is proportional to the velocity, means that is proportional to x dot. C is the constant of the damper. If we now add forces in x, we have the force of the spring, negative, the force of the damper, negative, and is equals to the acceleration that we assume to the right. If we put everything in one side of the equation, this is the equation of motion that we get. Very important that all terms are positive. Mass times acceleration plus the constant of the damper times the velocity plus the constant of the spring times the displacement. We do not have any external force, therefore the equation of motion is homogeneous. Now we'll do the equation of motion of a spring mass system that is in vertical position. At rest, that mass will hang in a position that is called the equilibrium position. In this position, the length of the spring is L sub 0, which is the unstretched length, plus a static deflection. That static deflection is an extra elongation that is due to the weight, which is mass times gravity. If we do the free body diagram, we will have the force of the spring that is opposite to the motion of the mass. So if we assume the motion going down, then we have the spring and the weight. Using the equation of motion, we add all forces in x. We call the x the direction in the vertical direction, just to use the same variable that we used in the previous example. And then we have the constant of the spring times the static deflection plus the deflection of the system when it's going to be in motion, vibrating, minus the weight. Since we already said that the static deflection is a consequence of the hanging the weight, we can say that K times the static deflection is equals to mass times gravity. So these two terms cancel out, and we get exactly the same equation that we got before in a horizontal system. Please note that the weight is not taken into consideration in this expression because it cancels out with the static deflection. So this is an equation valid when we measure x from the static equilibrium position. Now let's do the equation of motion of a spring mass damper system in vertical position. At rest, the mass will hang in the position called static equilibrium position. If we do the free body diagram, which entails the force of the spring, which is the constant of the spring times the static deflection plus the displacement of the mass, the force of the damper, in this case, is not proportional to the position but to the velocity. Therefore, is C, which is the constant of the damper times the velocity, and we have the weight. We add forces in the vertical direction, and we see that since the static deflection is equals to the weight, we can cancel out these two terms. Therefore, the equation of motion will be the mass times the acceleration plus the constant of the damper times the velocity plus the constant of the spring times the displacement equals to 0 because we don't have any external force. Of course, this equation is valid only when x is measured from the static equilibrium position. Therefore, we can cancel the weight. So for conclusion, anytime that we measure x from the static equilibrium position, we can write the equation of motion neglecting the weight, or just assuming that our weight it will cancel out with the static deflection. Now let's do the governing equation of an undampened single degree of freedom torsional system using Newton's second law. So here we have a disk that is hanged in a vertical rod. So the motion of the system will be with theta, it will be an angular displacement. If we do our free body diagram, this rod will behave as a torsional spring. The torsional constant of the spring will be this one right here, which is the shear modulus times the area moment of inertia divided by the length, and this is the area moment of inertia. Then we have the mass moment of inertia times acceleration. The mass moment of inertia will be, if this is homogeneous, is 1/2 mass r squared. If we add moments in the vertical direction, we have the moment of the spring, which is the torsional constant of the spring times angular displacement, equals to the mass moment of inertia times the angular acceleration. We put all terms in one side of the equation. We always get all positive components. This equation has the same form as the previous example. Now let's do the equation of motion of a simple pendulum of length L and mass m. It will have an angular displacement theta. If we use the normal and tangent components, we know that the tangent acceleration is the length times the angular acceleration, and the normal acceleration is the length times the angular velocity squared. remember that we can express our time derivative in terms of theta dot for the velocity and theta 2 dots for the acceleration. If we do our free body diagram, we will have the tension of the cord and the weight. And here, the kinetic diagram, we have the mass times the tangent acceleration and the mass times the normal acceleration. If we add forces in the tangent direction, we will not have the contribution of the tension, we will only have the contribution of the weight sine of theta in the negative direction that are opposite to the what I define as positive tangent direction, and then we have the mass times the tangent acceleration. So if we pass everything to the same side of the equation, we have a non-linear equation because we have here sine of theta. However, for small values of theta, we can assume that sine of theta is approximated to theta. This comes from a series of Taylor that I will cover in the next slide. Therefore, we have now the equation of motion as a linear equation where we have a component that multiplies the angular acceleration plus a component that multiplies the angular displacement. As you can see here, the mass can cancel out. And we can write the equation almost in this form. We will use the Taylor series expansion of sine and cosine to linearize our equation. As we said, sine of theta is approximately theta if we have very small values of theta. For vibration analysis, we always talk about small displacements, therefore we can neglect all the higher power values. For the cosine, we will do the same. We will take only the first term, and since theta is very small, all these values can be neglected. Therefore, we will use that sine of theta is approximately theta and cosine of theta is approximately 1. Let's do the equation of motion of a rolling disc. This disc is moving to the left because we have rotation to the left, and remember, for a rolling disc, the rotation means that also a displacement. There is no motion in the contact of the point of contact. Then we have the normal force, the friction force, and since we are moving to the left, then the forces of the spring are to the right. We do our kinetic diagram. We have an acceleration, which is the mass times the linear acceleration. This linear acceleration is a function also of the rotation of the disc, because in a rolling disc, the displacement is related to the rotation. The point of contact only has acceleration in the vertical direction. If we take moment respect to the point of contact so that we can eliminate these two forces, we can use this expression right here. The external moments, which is the two forces of the spring, so it's negative 2krx equals to the kinetic moment. The mass moment of inertia of a disk at its center of mass is 1/2 mass r squared, and then we have this term, which is this one right here. Therefore, we can write the equation of motion either in terms of theta or in terms of x. We have to choose one of the two variables. Both equations will give us the same result. Let's get the equation of motion of a bar that is rotating respect to a fixed point O and has two springs. If we take our coordinate systems as tangential and normal components, we have, for the pin, we have two reactions. We will assume that springs stay vertical for small angular displacements. Therefore, we have a force that is opposite to the motion for this spring and also for this spring. This spring is being extended and this spring is being compressed. Then we have an applied force at the end A, and we have the weight of the bar. We have that the spring 1 has a constant of 2k, and then we have that the displacement that this spring goes under is L4, which is this distance, sine of theta. The spring 2 has a constant of k, and since this length is 3L/4, the this deflection over here of that spring is 3L/4 sine of theta. Then we have the kinetic forces. We have an acceleration in the tangent direction of the center of mass, and we have a normal acceleration. The mass moment of inertia of point O, we will use the parallel axis theorem, is the mass moment of inertia at the center of mass, and md squared. D is the distance between the center of mass and point O. We will take external moments respect to point O, and that's equals to the mass moment of inertia respect to the point O times the angular acceleration. The external moments respect to point O, so we take moment respect to this point. The force of the spring one will create a moment. The moment arm is L4 cosine of theta. The moment arm from the weight is L half cosine of theta. The moment arm for this force is 3L/4 cosine of theta. And finally, the moment arm for this force will be L cosine of theta times the force right here. And in the other side of the equation, we have the mass moment of inertia respect to point O, the angular acceleration, which we can write as theta 2 dots. For small rotational displacements, we can substitute the cosine of theta by 1 and the sine of theta, theta. And therefore, this expression right here, we will put all the components that have theta in one side of the equation and all the independent terms in the other side of the equation. Therefore, we can write this term as 1/3 ml squared theta 2 dots. These two combines is 11/16 L squared K theta, and this is the independent term. We can write this expression as m equivalent times the angular acceleration, where m equivalent is this value, K equivalent and will be this value, which is 11/16 L squared K, and then all this term as a force equivalent. In this example, we'll do the equation of motion of this pulley that is rotating without slipping in this point and has two springs, a damper, and applied force at this point. The mass moment of inertia is given at the center of mass. In the free body diagram, we write all external forces, active and reactive. The active force is the weight and the force applied at this point. Then we have the system rotating about A. If we assume a clockwise rotation, there is this extension. Therefore, this spring is being extended and the force is opposite to the left. And in this case, since we are rolling respect to point A, this spring, the one below, is being compressed. Therefore, the force goes to the right. The spring for K2 will have this extension from A. We can calculate that this is 2r theta. And for spring 1, we can calculate that if we are rotating respect to this point, this spring will be compressed r theta. And the velocity of this point will be r theta dot. Therefore, the force of the damper will be the constant of the damper times the velocity. Now we do the kinetic diagram. We know that the pulley is rotating, and since this is the instantaneous center of rotation, we can relate the rotation with the displacement. We will have the mass times the acceleration of the center of mass. The point of contact has only acceleration in the y direction. We know that the external moments are equal to the kinetic moment. We will take moment about the point A. So this is the vector equation. This is the external moment. And we can convert that into a scalar equation where this is the mass moment of inertia of the center of mass times the angular acceleration minus this over here, which is taking moment respect to this point. This is the moment that creates this acceleration. Remember that the acceleration of g can be put in terms of x2 dots, but also, since it's rolling without slipping, is r theta 2 dots. If we take moment of all the external forces, we take moment at A. This spring is creating a positive moment and the distance is 2r. This spring is creating also a positive moment and the distance is r. The force of the damper is creating also a positive moment and the distance is r. And the external force is creating a negative moment and the distance is 3r. So the external moments are equals to the kinetic moment. And if we write all the terms that have theta or any of its derivatives to the other side of the equation, so we pass this negative to the other side and this goes to the independent side, we get the equation of motion. This equation of motion can be written in terms of a mass equivalent times the acceleration, where this is the mass equivalent, a constant of the damper equivalent times the velocity, the angular velocity, this is the equivalent constant of the damper, and an equivalent constant for the spring, and this will be the equivalent constant of the spring, and an equivalent external force, this one right here. We can also use energy method to get the equation of motion. We reviewed already that the potential energy of a mass will be positive if I'm above the reference or datum, and will be the weight times the height, or will be negative if I am below the datum. In the case of a spring, the potential energy is always positive, is 1/2 the constant of the spring, the stretch square. The kinetic energy of a rigid body in pure translation will be 1/2 mass velocity square. The rigid body in pure rotation would be 1/2 mass moment of inertia angular velocity square. And if we have a rigid body in general motion, we have to take into consideration the component of the translation and the component of the rotation. For a system that does not have any elements that dissipate energy, the kinetic energy plus the potential energy will be constant. So if we derive this expression, this is equals to 0, means that the total energy doesn't change. So if we do the same example, spring mass system, the potential energy of this spring is 1/2 constant of the spring, x squared, which is the displacement, and the kinetic energy is 1/2 mass velocity squared. If we derive both expressions, we get k, the displacement, the internal derivative, because we are deriving respect to time. The internal derivative is the velocity. If we derive the kinetic energy, we have mass, velocity, and acceleration. If we have conservation of energy, we have these two expressions, and as you see, because this is equals to 0, the velocity cannot be equals to 0, therefore we get this equation of motion. This equation of motion is exactly the same as the one we got using the Newton's second law. We can do the same process for the torsional system. We got the potential energy will be the potential energy of the spring. In this case, the spring is the bar that has a equivalent torsional spring constant. And here we have a kinetic energy, which will be 1/2 mass moment of inertia angular velocity squared. We derive both expressions, and again, we put the conservation of energy, and since the angular velocity cannot be 0 for all times, we have that this bracket has to be 0, and that becomes our equation of motion. We have done several examples, a mass spring damper system, a torsional system, a rotating bar, rotating disc, a cantilever beam with a mass at the end, and this is a pulley with 2 springs. If we see that we got for all of them the same second order differential equation. In the next presentations, I will spend some time solving this differential equation.